Okay, welcome everyone to my continuation of what are my favorite theorems. As usually, my favorite theorems, so take everything with a huge grain of salt, with a huge pinch of salt. Well, today's theorem is due to someone whose name I definitely will not pronounce correct. I give it a shot. Matiyasevich. So it's called Matiyasevich's theorem. And it basically is a theorem in decision theory. If you know something like Gödel's incompleteness theorem or Turing's halting problem, something along those lines, but in some sense much better, or at least in my opinion, much better, because it's concerned about some real problem in mathematics. I will show you. Let's think about, let's say, Gödel's incompleteness theorem. So what people usually do in the setup is they try to formalize something like the liar's paradox in a formal language. So the liar's paradox is just I am lying, which obviously, well, maybe not obviously, but it can't be true or false. Because if I would saying the truth, then I would be lying, right? That's my sentence. And if I would be lying, then I would say the truth. So this is a statement that just can't be true in, let's say, common language. And as soon as you can formulate something like this in your formal axiom system, then you're basically dead. You found a theorem that, or a statement that can't be proven, and it also can't be disproven because it's kind of in your system, neither true nor false. Okay, and it was a pretty brilliant idea. It goes back to people like Gödel, for example, to just formalize this in whatever kind of language, formal axiom system we have in mind, something like piano arithmetic. What is a little bit disappointing with those statements is that, yeah, well, it's a liar paradox, just formulated in an abstract language. So why should I care, right? So a language is not falling apart because I can say I am lying. And it's kind of the same for mathematics. All of these statements are usually very constructed, and it's not quite clear why this should be of any importance. Mathematics apparently, well, as you all know, mathematics is not falling apart because of it, right? So what is much more impressive, at least in my humble opinion, is if you can really find a statement which has influence in mathematics itself, and you can show whatever, that it's independent of your axiom system, that you can't prove it, that you can't find an algorithm, that's what I'm going to tell you about today, to solve it, and so on and so on and so on. And yeah, Matiyasevich's theorem is basically a good version, if you want, of something like Turing's halting problem. We'll have a look. So let's get started. So this whole, well, video is about Diophantine equations. So a Diophantine equation is something extremely simple and extremely important in mathematics. So here's, for example, one example. It's called the Pell equation. You have two variables, x and y, and you have kind of additional factor n, which you can specialize to anything you want. So let's say a natural number. And you're looking for solutions for this problem, right? You have two variables, x and y, and you're looking for, well, the solutions x squared minus n times y squared equals 1. So, so here, as you can see, I have x squared minus, so n is 2, n is 2, I just specialized n, x squared minus 2y squared equals 1. And this is how the graph looks like. And the first observation you make is, okay, this is a polynomial equation. So in an appropriate field, in an appropriate setup of numbers, you will have infinitely many solutions. And then what really matters is kind of the geometry you see here. Like this is an hyperbola, as you can see. It's an hyperbola, right? Here you go. But that's not quite the question I would like to address. That's more part of algebraic geometry. No, I'm kind of trying to address a more basic, in some sense, question, at least a more classical question. So Diophantius and others, and this certainly goes back to the old Greeks, were more interested in the points you can see here. So it goes back to the old Greeks. So let's say 2000 years. And these points are different from all other points because, so I have 6 of them, because they are integer solutions, right? So x in this case is 1, for example, and y is 0. And yes, if you feed this in here, you get x squared minus 0 equals 1, and x is 1. So yes, this is a solution. So those Classical questions, so Diophantine equations, are just polynomial equations, but you don't want to solve them in a geometric setup, so over an appropriate field, whatever complex numbers, whatever comes to mind, but rather in a, let's call it a number theoretical framework. You want to solve it over something like the integers or the natural numbers, which is kind of equivalent. So whether you want to solve it over the integers or the natural numbers, you already can see here's a certain symmetry between the solutions. In general, the symmetry is a bit more complicated, but in some sense, you can reduce the problem, in some very precise sense, you can reduce the problem of solving such an equation in the integers by finding an appropriate Diophantine equations, which you then solve in the natural numbers. So kind of what we're doing here is we're looking for natural number solutions of polynomial equations. Okay, that's a super classical problem. It's so super classical that all of you know at least two examples of this. They're kind of the same example. It's kind of a very fun flavor of the same example. I will comment on that later at the end of the video. But basically, well, kind of the easiest non-trivial thing you could try would be something like x squared plus y squared equals z squared. And you want to solve that in integers. And what you end up with is, of course, this picture, right? So here is z, well, maybe I should write a new one. So here's z, of course, and here is whatever. Let's say here's x and here's y. Right? The solutions to this problem are called Pythagorean triples, for the obvious reasons that you just see Pythagoras' theorem on the right-hand side here, right? And yeah, this is definitely a very classical problem. Even if you don't know anything about the history of mathematics, I think it's very convincing to say that this is a very classical problem. The generalization, which is so well known that it actually appears in The Simpsons. So here you can, it's a very classical one. Here you can see Homer's attempt to solve this equation. This is, by the way, not a solution. You can try it. This equation doesn't work. It's something called a near miss. So it almost works, but it doesn't work. So Fermat's last theorem says then whenever n is, so n is again something I can substitute, for example, n equals 3 or n equals 4, whatever. Whenever n is not 2, and the 2 is this case, then there are no solutions. And that's exactly the question I would like to ask. So given the Diophantine equations, can I actually decide whether there is a solution? And by solutions, again, I say it again, I mean something, let's say, in the integers or in the natural numbers. Because it's a polynomial equation, you will always find solution over an appropriate field. I don't care, or at least for this video, I don't care. I'm interested in finding solutions over the integers. And I mean, this is a very, 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 very classical problem. And you can already see that it can't be so easy because, well, this got solved, whatever. The problem here got solved probably 2,000 years ago, something like that. The old Greeks were probably already aware of those solutions. Fermat's last theorem, well, Fermat, of course, claimed he has solved it, but I don't think anyone really believes he has solved it. We don't know. We will never know. But a more formal theorem is due to Andre Wiles in the 90s. So it's about 30 years old by now, if you're watching this video in 2021, of course. So 30 years old compared to 2,000 years. That's basically, it was basically proven yesterday. And it already shows you that even this simple question, so I'm only asking, I'm not asking list all solutions or something like that. I'm just asking whether there is a way to just decide by, oh, I have my Diophantine equation. Can I actually decide whether it has a solution or not? Very simple-minded question. Turns out that the answer is amazing. So let's have a look. Not quite. We need to do something before. So let's come back to our Pell equation here. And the only thing I did is, of course, I can list all solutions by brute force. I can do that, and I don't care whether this would take an infinite amount of time. In principle, it would take an infinite amount of time. I can basically list all solutions. What can I do? For the Pell equation, for example, I can just fix y and let y run through all the natural numbers, say. That's what I do here. So y in this example runs from 0 to 10. Of course, 10 is just an arbitrary break. I could let it run further. And I just solved the equation, which is now very simple. So I fixed all variables except one, and I solved the corresponding equation, which is then very simple. In particular, for computer, it's very simple. And I just collect all the ones where x is also an integer or a natural number. And I would reject all the other ones. So here is x apparently wants to be square root of 3 or whatever, square root of 19. You get the pattern, right? You just throw away everything else. Okay, so I certainly can always solve the Diophantine equations by brute force. Given an infinite amount of resources, I potentially could do that. The real problem is if there are no solutions, then kind of my algorithm wants to run forever. This brute force algorithm. So basically the question is there any way to do better in general? Right? That's basically the question. And I stress it again, I'm not asking for more sophisticated questions like, can I list all solutions, or do I have it? So this algorithm here is, of course, hopelessly inefficient. It's forget it. Don't do that. Right? Don't do that in practice. So I'm also not asking for an efficient algorithm. I'm just asking for an algorithm. And I'm also not. I mean, even an efficient algorithm would be something like an algorithm that is as efficient as possible. Maybe you can prove by abstract theory that an algorithm has to be of a certain complexity. And this complexity is still astronomical, like whatever, it grows by n factorial or something like that. Maybe n factorial or something. It grows super exponential. It's just crazy. So that's an efficient algorithm because you just proved that it can't do better. You can't do better, but that's not an algorithm that works in practice, right? So the third question is not quite the same as the second one. Just keep it in mind. But I'm not going to address them anyway. So let me say it again. I'm not interested to find all solutions. I'm not interested to find an efficient algorithm. I'm not interested to find something that works in practice. I'm just asking a very naive question. Given a Diophantine equation, is there a way to decide? Is there any algorithm, anything you can run on your device you're watching this video right now that can decide whether this Diophantine equation has a solution or not? Seems to be a very simple question, and the answer is, well, exactly Matiyasevich's theorem, which is an extremely amazing theorem. I've put a lot of links in the description because it's really worthwhile to read it from different perspectives. I put some nice things to play around with in Mathematica in the description as well, if you want to test them. But basically what the theorem says is a set is listable if and only if it's Diophantine. And those two words, well, you maybe already guessed what Diophantine might mean. So Diophantine means it turns up as a solution. So the set is exactly the solution set of a Diophantine equation. It's exactly what I did before. This is Diophantine. A listable means there is an algorithm that enumerates the members of your given set D. And I just showed you one of the directions, namely, if it's Diophantine, it is listable. My algorithm was very stupid, but keep in mind, I don't care whether this runs very fast or not. I'm just interested in finding an algorithm. And the theorem, actually, the real meat of the theorem is this way. So everything that you can list by an algorithm actually turns up as a solution of some Diophantine equation. And that's tricky. That's not easy. That's Hilbert's 10th problem. So it basically, it was solved in the 70s then. So it took a long time to get solved. And it's just extremely amazing. I show you an explicit example in a second, what this actually means in practice. But the crucial implication is that there is then no algorithmic decision procedure to determine whether a given Diophantine equation has a solution. In other words, this theorem justifies why people are struggling to find solutions to Diophantine equations. Because in general, there is no procedure. Right? It's kind of completely different from the question to find all solutions or whatever. I'm just interested in finding one solution. And it turns out that in general, I just can't. And the main ingredient is that there are certain non-decidable sets. All of them are listable, but there are certain non-decidable sets, and they all come from different version of Gödel's incompleteness theorem. Precise link is in the description if you wonder how this actually works. Yeah, so listable if and only if Diophantine. So you can find an algorithm that enumerates members of D if and only if you can find a Diophantine equation, a polynomial that solves that. If you solve it, well, if you look at its integral roots or its whatever integral roots, or I'm using natural numbers here, as I explained, it doesn't really matter. So if you look at the natural roots of it, then that's exactly the members of your, those are exactly the members of your list. Again, I say again, a lot of funny references are in the description to make this more precise. But to give you a fun application, it's kind of an application, why this direction from the one that is hard, not the one that I showed you. This one is silly, right? This one was easy. No, the hard one. Why this is actually a really surprising and strong statement. So everything that is listable, for everything that is listable, you should be able to find a Diophantine equation solving it. An example of a listable set would be primes. So prime numbers is a listable set. Think about it for a second. That's not so hard. You just need an algorithm that spits out prime numbers. That's not so complicated to find. And this theorem now tells you that it's not completely stupid to look for a polynomial or Diophantine equation that spits out prime numbers. So the solutions are exactly the prime numbers, which is, I mean, this is ridiculous. And people did that. So here's a famous paper. It's called Diophantine representation of a set of prime numbers. It's exactly what I just explained. It's, well, if you want to pause the video, it doesn't really matter. I link a Wikipedia page in the description where you, I think, can find exactly this polynomial. So this is a Diophantine equation in God knows how many variables. I probably could just count, and God knows of what degree. And the point is, the roots of the natural number roots of this equation spit basically out the set of prime numbers, which is pretty amazing. And how does it work? Well, so I have j variables here and I have y variables here, but actually I could just say I have an a here and I have other variables here, and this a then varies if you fix a certain value here. So this a variables varies and spits out the prime numbers. So this is how this works. But anyway, this is a very surprising statement. Right? Everything that you can list, you can in principle find a Diophantine equation solving it, which is kind of fun. And they actually mention him. So Matiyasevich, as I said, but also he strongly builds, and I should have said that at the beginning, but I wanted to wait for this page because I always forget the names. He also built strongly on the work of Davis, Putnam, and Robinson. That's why it's sometimes called, in certain order, the DMPR theorem. So what I just called, at least for today, what I called Matiyasevich's theorem is sometimes called DMPR, or in some permutation order of DMPR, because Matiyasevich strongly built it on the work of those other three people. And what is done in this paper is then they say, oh yeah, by the way, they show that every listable, there's a different name for listable, recursively enumerable set, is Diophantine. That implies, by the way, that primes are Diophantine. So let's try to find a polynomial that does the trick. And yeah, here's the polynomial, which is a bit ridiculous because this is not a good way of doing this in practice, by the way. But that's not the point. The point is it's kind of fun that you can find a polynomial that solves for primes. And it turned out to be a bigger business. So there are several other known polynomials that solve for primes. I think Wikipedia lists, linked down in the description, lists quite a few of them. Yeah, anyway, I hope you enjoyed this video today, which was kind of an application of Gödel's incompleteness theorem. So it's built in. As I said, it's built in over those non-decidable sets. but it's kind of a real world application of Gödel's incompleteness theorem, in the sense that it addresses a very, very classical question in mathematics, whether you can solve um, Diophantine equations. So to end this video, let me come back to my this picture, to Homer versus Pythagorean. So Pythagorean triples versus solutions for x to the n plus y to the n equals z to the n for n equals 2. And this complicated Fermat theorem is basically concerned about n greater or equal to 3, which, as we know by now, is actually no coincidence. So actually, you can make Matiyasevich's theorem stronger by saying, as long as you have a Diophantine equation of order at most 2, you actually can find an algorithm, right? So we don't know what happens from 3 onwards, but for 2, you always can find an algorithm. So 2 is a much easier thing to consider than everything else, which fits beautifully to Fermat's last theorem, because, as I said, Pythagorean triples, the n equals 2 version, was known for 2,000 years, while it took quite a while to prove that there are no solutions for n bigger or equal to 3. Yeah, but in anyway, I really hope you enjoyed this video, and I also hope to see you next time.